second season of Ithaca Fest. So I think we can start. And today I will be your chair, and the first speaker of the day again is Martina Rovelli. She's going to talk about an explicit comparison between globular and simplicial models of infinity to categories. Martina, you can start sharing your screen whenever you want, and I leave the stage to you.
Thank you very much for the introduction. There we go. Yeah, thank you for the introduction, for the invitation, but also for kind of setting up this group. I think it's cute and it's a really nice idea. Like, for instance, there are a lot of people that I have not met in person yet. So I think it's really nice. Thanks. Okay, so as it's given away by the title, the result that I would like to discuss with you today is about an explicit comparison between two given models of infinity 2 or even infinity n categories. That is work in progress that we are writing up right now with my collaborators, Julie Bergner and Victoria Ozornova. I understand that we are all category theorists in this group, but I was not sure about how much familiarity I should assume regarding the higher side of things. So I'm not planning on giving a like really hardcore technical talk. And instead, I hope I will be able to kind of give an idea to everyone about what is the type of the result and what are the questions that maybe we care about in this part of the subject. And stop me at any time for questions. Okay, so maybe as a little introduction, if we want to try and understand how one might end up doing higher category theory from strict category theory, the starting point, the main observation is that the theory of ordinary categories and of strict n categories is an established thing. It has its own examples, theories, and we are all very convinced that this makes sense and it's important. However, it has limits in that there are situations in which we really feel like certain things should behave like n categories, but they don't quite work. They seem to present the correct structure, but the axioms are not verified. And so there could be a complaint that says this theory of strict categories is too strict. It doesn't accommodate examples that we care about in homotopy theory. And therefore, the response is that you will want to generalize the notion of an n category and get to an infinity n category. The problem, though, is that even though you understand roughly what an infinity n category should be, it's not straightforward how to generalize the strict concepts. Like, there's too much freedom, too much room for interpretation. And the manifestation of this fact is that it's hard to give a precise and well-defined notion of what an infinity n category should be. In particular, people who like different techniques or like from different school will respond in different ways and declare that an infinity n category is given in a model rather than in another one. And if we want to be able to compare the two approaches and kind of speak the same language, it's really important that, yes, we develop different models, but we also understand how to go back and forth as explicitly as we can, so that we can be able to import and export theorems proven in different setups. And there are a lot of different models of infinity n and infinity 2 categories. I am not planning on giving a list. I just want to mention that the two models that I will care about for today are Verity's saturated n-complicial sets and Rezk's Θn spaces. Now, if the theory is well behaved, what you would expect is that these are two different words that are equivalent in some sense. But this is not a theorem. At the moment, this is just an open problem. It's an expectation. And if you want to report on the status of this expectation, this highly depends on the value of n. And so we have a little chart that tells us that when n is small, namely 0 and 1, work by Rezk essentially tells us that there is nothing else that needs to be done. And we know that when n is 0 or 1, the two models are equivalent, and we understand very well how to go back and forth. And in the second row, when n equals 2, a positive answer only came essentially last year, where the work by Gagna, Harpas, and Lanari, together with a lot of work that had been done before by many different sets of authors, but now I will just mention Lurie and Bergner and Rezk, allowed us to conclude that for n equals 2, the two models are indeed equivalent. And although this is a great result, there's still a lot of work that needs to be done. So first of all, we have a question mark for n that is higher than 2. And even when n is equal to 2, if we want to be able, as I was saying, to go back and forth between different models, we not only care about knowing that the expectation is satisfied, but also we want an explicit comparison between the two. So you may add a second column here that kind of refines the conjecture and looks for an explicit comparison. And Rezk's work is enough to say that we are good for n equals 0 or 1, but up until now, the existence result was not enough to have an explicit map of translation, because the fact that the comparison, that the equivalence is true, is going through a lot of different results that are virtually impossible to track down. And the result that I want to, we have been spending a lot of time trying to address these two question marks. And what I want to say for today is that this question mark is now a check. And this is this work in progress with Julie and Victoria that I mentioned in the beginning. So the theorem, in a very informal way, could be phrased by saying that we do have an explicit comparison in the case n equals 2, so between saturated to complicial sets and θ2 spaces. And ideally, a long-term hope and goal would be to also make everything work also for higher n, but there's still a lot of work to be done in that direction. So the long-term hope would be address n at least 3 or higher to obtain an equivalence between the two models. Okay, so the way that we prove the theorem, like most of the results that I have mentioned over here, are in the language of model category theory, and they have a lot of technical aspects that I am not planning on kind of going through. So what I will be explaining is kind of the surface of the argument. And I thought it would be good to, before starting talking about comparison of models of infinity 2 categories, to take a step back and see a little bit of what the picture looks like, even for infinity 1 categories, in case you have never seen them. So for this, maybe the starting point is, what is an infinity 1 category? And what I'm giving you at the moment is just a philosophical definition, what we expect from such an object. An infinity 1 category consists of objects that we think of as 0-dimensional morphisms, but also has morphisms in every dimension k that go between k minus 1 morphisms. And we also expect that these morphisms will compose in some way. So that compose weakly. And we also expect that in dimension 1 or higher, they are going to be invertible. And invertible for k bigger than 1. So the type of structure that we have is that we have some objects that we think of as dots. We have some one-dimensional morphism, and whenever I have two parallel ones, I may have a two-dimensional morphism. And when I have two parallel ones, I may have a three-dimensional morphism. And the requirement is that, for instance, this one has to be invertible. So in particular, the one that you see here is the one that you see here. So you can already guess what an infinity n category would be. Now, this does not qualify as a nonce definition for many reasons. It's messy, it's circular in a lot of ways, and it's more of a guiding principle. It's an asset of properties that we have maybe found in concrete examples, and whenever we will manage to get to a precise definition, we expect this structure to be present. So here are some easy examples or situations that you may have encountered. There are also much more like sophisticated ones, but these are more like toy examples. So one situation that you may have is that you have a topological space X, and then you can think of the points of X as zero morphisms of something that looks like an infinity one category, and then you can have paths between these points, which would look like one morphisms. And then you can easily guess that there is some two-dimensional morphism, which will be given by some homotopy of paths. And we can already see that ordinary category theory would not be sufficient for this situation, because when you try to compose paths, you can concatenate them, but this operation will only be associative up to a path homotopy. So we are in a good place. An example of a different flavor would be a situation where I take as zero-dimensional morphisms just sets. Maybe I have A, B, and C. Here are three objects. And maybe I want to take as a morphism a span. And you may have noticed that whenever you have two consecutive span and you try to compose them, you kind of have a well-defined thing, but only up to isomorphism. So this suggests that we should take into account this two-dimensional information and add as two morphisms, isomorphisms of spans, which we could draw here. And finally, a more geometric example is a situation where the objects are closed one manifolds. So here is one object, and here is another object. And then a morphism could be a cobordism between such. So here is the usual pair of pants with maybe a hole. And if I have two consecutive ones, so for instance, if I have a situation like this, you can imagine that you should be able to compose them just by gluing these cobordisms together. But again, you're going to run into the problem that this operation is not associative on the nose. It will only be associative up to a diffeomorphism of cobordism. And so you can include this two-dimensional information. So these are three different situations that you may have encountered where you do feel like this higher information is present, and where you also need to weaken the axioms that define what a higher category is. But now if you want to do math, you need to sit down and write a definition that would make it into an article. And there are different responses that, that you can obtain. So here's one. One way of trying to do math with this stuff is to say, okay, from now on, for me, an infinity one category is going to be a topological category. And now you may or may not know what a topological category is, but the point is this is a well-defined notion, and you can prove stuff about it. So what is a topological category? It's a category enriched over the category of topological spaces. And roughly speaking, what does it consist of? So it still looks like a category. So it has objects that maybe we call A, B, and C. And then rather than having just a set of morphisms between objects, now we have a space. So for instance, A and B are two objects, and between them, I will find map AB, which is a space. And I also have, as part of the structure, a composition operation that is compatible with this topology, with this topological space. So plus compatible composition. Okay, so in principle, I could read this definition ignoring all the introduction that has come before it, but what does this have to do with the requirements that we had set up for ourselves? So we can observe that if I have my space map of AB, this is my space, Whenever I take a point in here, I can read this point that I'm suggestively calling F as precisely the one-dimensional type of morphism that I expect to find between A and B. And whenever I take another point here that I'm suggestively calling G, then this will also give another one-dimensional morphism that is parallel to the previous one. And now the topology of this space is telling me how to read the higher dimensional information, because whenever I'm able to draw a path alpha between these 2 points, I'm allowed to regard this as a 2-dimensional morphism. So I have read from the structure of a topological category the existence of higher information alpha going from F to G. And I can also give an interpretation to the fact that it's invertible, because you can think that you can always reverse a path. So this is one way of making sense of the axioms that we were hoping to implement. A small observation is that we are indeed recovering strict ordinary one category theory, because if you start with a normal category, you can always make it into a topological category with an uninteresting topology. Namely, you can just keep the same objects and you take discrete mapping spaces. Okay, so this is one approach, and you can just develop the theory as much as you want and continue your way. Instead, let's take a break and let's observe a different approach that one could take. So here's a definition 2 that is a priori completely independent from the previous one, which is, okay, now an infinity one category for me is a quasi category. And again, you may or may not know what this is, but this is an established notion that, as opposed to the previous one, which would live maybe in a book about enriched category theory, this one would rather live in a book of maybe simplicial homotopy theory. It's really about simplicial sets. So what is a quasi category? It's a simplicial set in which inner horns have fillers. So if you have never seen this notion, what does this mean, kind of speaking informally? So the fact that it's a simplicial set says that the type of structure that I have is that consists of a bunch of vertices bunch of edges and a bunch of triangles and a bunch of triangles of a higher dimension. So maybe here are some vertices that, of course, I'm thinking as objects of my infinity one category. Then I would have some edges between those vertices. And maybe whenever I have the boundary of a triangle, the triangle is indeed filled. So I have my simplicial set, and the condition that inner horns have fillers in particular tells you, for instance, that whenever you find a configuration with 2 consecutive edges that I'm thinking of as 2 composable one morphisms, then there will always exist some 2 simplex that you can fill in sigma. And what is the interpretation that I should give to this fact? Well, I should interpret, so it has 2 things that I want to observe. One is that I have the presence of some higher dimensional information, and one is that I am kind of able to compose one morphisms. So maybe the way that I want to write this down is to say that whenever I am in a situation like this, then I want to read this as sigma being some invertible 2 morphism from H to G composite F. So this is a different approach from the previous one, but in both situations, we had a mathematical object where we were able to compose morphisms. Sometimes it was easier than others. For instance, here it's slightly obscure how to compose morphisms. And in both situations, we had higher dimensional information. Like before, it's not a mystery how to obtain a quasi category from any category C. And this is the well-known nerve construction. So if I have a category C and I want to tell you how to build a quasi category nerve of C, I can just tell you that the set of n-simplices is given by the chain of n+1 n-composable errors in C. So I can use ordinary categories kind of as a playground to test the theory of quasi-categories that I might be building. Okay, so what can we say about these two different approaches? So maybe if I'm trying to choose what is my favorite ones, I could write down a little table about aspects that I might care about. So here I wrote very easy ones, but again, you may have a very special and complicated needs. So here I just recorded for each of the two, whether it's easy to recover ordinary categories, whether it's easy to recover spaces. We saw that the space should be an example of infinity one category. So can I incorporate this example into the model that I'm studying? And finally, is it easy to compute what is the composite of two one morphisms? And so maybe, as we mentioned, it's particularly easy to build an infinity one category in both models starting from an ordinary category. So maybe this is a tie. But if you're trying to build an infinity one category from a space, you're going to have a much harder time if you try to do it with topological categories. And so for this one, we give a point to the quasi-categorical model. Of course, eventually the two things are equivalent, so you can find ways to do it, but it's a less straightforward and transparent process. And instead, if all you care about is understanding perfectly how to produce a composite for morphisms, then you probably would prefer the topological category approach, because in their composition is part of the structure, so you don't have to bother very much to find it. And instead, if you're trying to compose one morphisms in a quasi-category, you don't even have a composition function. You just need to, you need to go and evoke the existence of a filler, and it's not a unique thing. So the point that I'm trying to make with these small examples is that there are situations in which one of the two models is better than the other one. And maybe the comments are that, first of all, the models are indeed different. They were both designed to model the same phenomenon, but in practice, they have different points at values. And I don't want to give up any of the two, because we have seen that for certain features, one of the two is better, and I don't want to lose it. And for this reason, it's important to keep both and understand how they compare to each other, because if I want to prove whatever property regarding composition of one morphisms in the model of topological categories, I want to be able to export any relevant construction and any relevant statement that I have proven to the other model. Okay. So how do we proceed? And here are two typical theorems that you would prove when you're trying to kind of study how models compare to each other. So the first step normally is to gather all objects of the same kind into yet another infinity one category that is, however, larger. So Theorem A says that there is an infinity one category Q cat, where the objects are quasi-categories. And the way that you would build such a thing is that you would build a model category of in which the fibrant objects are quasi-categories. And in this case, this comes from the Joyal model structure. And there is also an infinity one category of topological categories that comes from the Bergner model structure. So this may look circular in a way, because we are putting together infinity one categories and we're producing another one. It's not circular. There is a way using model category theory in which you can make this precise. And as category theorists, you should also not be surprised that, I don't know, when you put together all categories, you do obtain a category of a larger size. So this is a similar phenomenon. And now that we have established kind of a moduli space of all quasi-categories and the moduli space of all topological categories, you do want to compare them. So this is what Theorem B is for. Several proofs have been given of this theorem, so maybe let's mention.
Sorry, can I ask a question about Theorem A?
Sure.
So these are infinity one categories, but wouldn't it be more natural to gather them in infinity two categories? And for that purpose, model categories wouldn't be enough, I guess.
So if you want to go to infinity two categories, this is definitely something that we and people in general want to understand. If you want to treat that aspect with model categories, then you would look for, first of all, a model category, and maybe you want to check that it's enriched over itself. So once you recognize, say you have the Joyal model structure, you recognize that every object of this is an infinity one category. So if you manage to enrich it over itself, then you would obtain that between any two objects, you have an infinity one category. So this would be a way to recognize it as an infinity two category. So the short answer is there is a way to do it, but in a way you need to address the infinity one categorical level first.
Okay,
this
thank
is the
you.
way I see it. Yeah. Okay, more questions? Okay, so I was saying Theorem B is meant to state in which way the two approaches are equivalent. So there are different proofs. I think there's one by Joyal and one by Lurie and one by Dagger and Spivak. I'm probably forgetting many. So there is an equivalence between this Q cat and between this top cat as infinity one categories. So this is good because we can read Theorem B as, in this sense, the two models are equivalent as infinity one categories. So they are not the same thing. It's not like if you start with a quasi category, you have a unique way to, a unique and canonical way to produce a topological category. But the freedom that you have will always live into a contractible space of choices, kind of. Okay, so this was just a very superficial overview of what the picture looks like for infinity one categories. This is something fairly understood by now, but maybe we want to reuse the same pattern, the same like scientific method to now try and understand infinity n, and maybe we start with infinity two categories, which is already hard enough. Okay, so there we go. Models of infinity two categories. So this is something that I have copied from before. This was the guiding principle for the notion of an infinity one category. It had objects and morphisms in every dimension, and we were expecting to be able to compose them, and we were expecting invertibility starting in dimension 2. But as I have anticipated before, now we want to allow larger generality, and now we want to talk about an infinity 2 category, which means you may have non-invertible two cells. Okay, this looks like an innocent change, but there is a significant augmentation in difficulty in like, trying to study infinity 2 categories as opposed to infinity 1 categories. So just as a maybe small motivation, we can already realize that 2 of the 3 examples that I mentioned before actually were a reminiscence of an infinity 2 category rather than an infinity 1 category, because maybe I don't only want to consider isomorphisms of spans, maybe I just want to consider all morphisms, maps of spans, all commutative diagrams. So not necessarily isomorphism here. So if I perform this change, which is maybe more natural than the one before, then what I have is rather an infinity 2 and not an infinity 1 category. And in the same vein, maybe like we had only focused on diffeomorphisms between cobordisms, but a cobordism is a manifold itself. So why not considering cobordisms of cobordisms, which is a more natural and coherent approach. So this already says that it may be relevant not to restrict yourself to infinity 1 categories. And moreover, we could maybe add, as it was mentioned a moment ago, an extra line to this to say that infinity 1 categories in whatever model should form an infinity 2 category with an appropriate notion of functors and natural transformations. So as it happens for ordinary category theory, if you want to really understand categories, at some point you need to get your hands dirty and understand the 2 category theory. And in the same situation, if we really want to understand fully infinity 1 category theory, we need to understand infinity 2 category theory as well at some point. Okay, so I'm hoping that we are motivated enough that it is relevant to understand infinity n for higher values of n than 1. And so then we take the same path as before. There are very many models of infinity 2 and infinity n categories. And one is the model by Verity, which says an infinity 2 category is a saturated 2-complicial set. And I'm not going to give you the full list, like the complete definition for this object. All that I want to mention is that it is a simplicial set, so something that we are not scared of. And the extra structure that is required is overall reasonable. So in which certain simplices are marked in positive dimension. Of course, satisfying suitable axioms. So it's not that I can choose a random set of marked simplices, but if we forget about the axiom, the underlying structure is rather easy. So we have a simplicial set, something that we understand, and the extra information just consists of a list of which n simplices are marked for every n in dimension 1 or higher. And if you are more familiar with Lurie's approach, there is a very similar framework. He calls them infinity bicategories. And the main difference is that he doesn't mark simplices in all positive dimensions, but just in dimension 2. So it's even a simpler structure. Okay, so I'm not telling you what the axioms are for this marking, but I will tell you how to construct a saturated 2-complicial set from any 2 category. And maybe if you understand this construction, you can have a little inspiration of what the axioms would look like by mimicking what is satisfied by this construction. So whenever we take a 2 category D, we construct a saturated 2-complicial set that we are denoting with this natural nerve of D. And it goes as follows. If you have ever encountered the Dusky nerve of 2 categories, this is the underlying simplicial set. So it's a 3 coskeletal simplicial set, and I just need to tell you what are the 0, 1, 2, and 3 simplices. The 0 simplices are just the objects of D, unsurprisingly. And also unsurprisingly, the 1 morphisms, sorry, the 1 simplices are the 1 morphisms of D. And a bit more interestingly, we need to choose what are the 2 morphisms of this nerve. And they are precisely 2 cells in D, like this alpha, namely, they are 2 morphisms with a specified factorization of the target. In this case, we are factoring through this object, D1. And you can see what a 3 simplex looks like. It consists of 4 2 morphisms of D that have boundaries as depicted. And the condition is that when you paste these 2 and when you paste these 2 in D, you obtain the same result, the same 2 cells. So this is a simplicial set If you recognize it, good. If you don't, it doesn't matter too much. I have to tell you what the marking is. So the easy thing to say is, I don't know what that's already filled. The easy thing to say is that you don't have to worry about high dimension because everything is marked in dimension 3 or higher. So that's easy. I only have to tell you when a 1 simplex is marked and when a 2 simplex is marked. And as it is shown here, a generic 1 simplex would look like this, and I am declaring that it's marked if and only if F is an equivalence.
Martina, sorry if I interrupt you.
Yeah,
I just wanted to mention that you have 10 minutes from now.
Yeah.
10,
Okay.
11, it doesn't matter, but more or less that's the time.
Yeah,
So,
thank you.
Sorry for interruption.
No, if I end up going late, let me know, but thanks. Okay, and when do I mark a 2 simplex? I mark a 2 simplex when the alpha, the 2 morphism that inhabits the 2 simplex, happens to be an invertible 2-cell in D. So you can already see that, for instance, the fact that when you compose equivalences in a 2 category, you still obtain an equivalence can suggest how some of the axioms might go. But I'm not going into there. Let me know if you would like to know more. Okay, here's a different approach due to Rezk. And now we say that an infinity 2 category is a θ2 space. So what is a θ2 space? It's a presheaf and the indexing category is Real's category θ2, and it's valued in spaces. And there are axioms again. And instead of telling you the precise definition of what the category θ2 looks like, I will tell you a couple of conditions that will help you get an idea. So first of all, it's a full subcategory of 2-cat. And the generic element looks like this. I have a bunch of points. This is a 2 category that I'm drawing for you. And then I have sequences of composable morphisms vertically. So for instance, the one I'm drawing for you is a generic element of θ2. You could have longer chains horizontally or vertically. And in particular, if you take somewhat degenerate pictures like the one I drew, you recognize that in θ2, you also find these 2 category, the free 2 cell, these 2 category, which is the free 1 cell, and these 2 category, which is the free 0 cell. Okay, and you can obtain, again, a nerve from any 2 category D. And the way you would do it is that whenever you evaluate to an element theta of θ2, you're going to look at all possible functors from theta into D that are lax and normal. And like before, you could write down certain features that you care about. For instance, some constructions that you may want to do in each of the 2 models is understanding how the op-dual construction works for infinity 2 categories, or the co-dual, or the join, or the gray tensor product. And like before, there's gonna be like different answers. So for instance, both models are good for treating the op-duality, but only the θ2 model is good for treating the co-duality. The join is kind of bad in both, but it's a bit better in here. And the gray tensor product is reasonably understood in both. And one important line that I may want to add is, now we are treating infinity 2 categories, but what if we wanted to treat infinity n categories? So treat infinity n categories for higher n. And in this situation, I consider the winner the complicial model, because although you can consider θ3, θ4, and θ5 spaces, it becomes very complex to even give the datum of a θ5 space, whereas the complexity of giving an infinity 5 category in the complicial model substantially does not change. And so, like before, we acknowledge that the approaches are different and that we want both, and we want to understand how they compare. This is really like copied from before, and it's the same story. And like before, the first step is to put them all together and build infinity 1 categories. So in this case, this was done for n-complicial sets. First by Verity, and then Victoria and I spelled out the details for the specific model structure that is needed, and by Rezk for Θn-spaces. And so Theorem A is good. Theorem B would say exactly that there is an equivalence of infinity 1 categories between n-complicial sets and Θn-spaces. The problem, and this would establish that they are, like before, equivalent models of infinity n categories. The problem is that Theorem B is not a theorem, but it's only a conjecture, which I think everyone believes, but it's not proven yet. And so this takes us back to the preview that I had given before, that whether the theorem is a theorem depends on n, and we have like the fact that the models were equivalent had been established before, but we now have an explicit comparison between the two models. And so this is the result, essentially. And I had prepared a box to say a few words about what goes in the proof, but you can stop me at any point from now. So I will just talk and you stop me at any point. So the way that we prove that there is an explicit equivalence, an explicit comparison between the two models, is by considering two different functors that have like orthogonal good properties. So on the one hand, we define a functor L that is new and very explicit. So explicit means that it really comes from a Quillen functor at the level of model categories, and there is no zigzag involved. And this is like as explicit as it gets. And if this speaks to you, I can tell you what is the value on representable presheaves. So if you take some theta living in θ2, then L sends it to the natural nerve that we have encountered before. That's one thing that you can do. Instead, you can also kind of package together all the previous equivalences that have been proven to produce another functor from θ2 spaces to two complicial sets. But this is long and painful. So in particular, you need to go through, so on this side, you need to go through infinity by categories with the equivalence by Gagna-Harpas-Lanari. Then you need to go through, what is in there? I guess marked simplicial categories through Lurie's Quillen equivalence. And then you need to go through complete single spaces and enriched categories. And this is Bergner and Rezk. And this is even more painful than it looks right now, because some legs, like this one, are not even a direct leg, but itself it goes through 3 intermediate steps. So you can call this F the composite of all of these. And the advantages or disadvantages of this F are, on the one hand, is that it's a known equivalence, because each of the steps individually is an equivalence of infinity categories, but it's not explicit at all. And what we do to conclude that we do have an explicit equivalence is to prove that as functors of infinity categories, they are isomorphic. So if we achieve this, then we can say that this functor is at the same time an equivalence and an explicit functor. And
unfortunately, Martina, I have to stop you here.
Sure.
So I would
Thank
like
you.
to thank Martina for this talk. Thank you very much. And we have silent applause, so we cannot show you our interest for the talk, but I think questions now will show you that people found it interesting. So if someone has questions, please unmute yourself and speak freely.
I do have a question. Can I go ahead?
Mm-hmm.
So first of all, thanks for your talk. If you could go just slightly above the slide you're at now, on your notes, at some point you mentioned a nerve construction with involving lax functors.
Mm-hmm.
There, so essentially you're looking at objects in θ2 and lax normal functors out of those. So I was wondering why the choice of lax, and is it because by looking at delta inside θ2?
You mean lax as opposed to aplax, or lax as opposed to strict?
Lax as opposed to, say, pseudo. But so the answer that I gave myself is that if you look at delta inside θ2, you can recover orientals in this way, so simplices. Is this the reason why you do that? Or maybe can you just expand a little bit on the choice?
Yeah. So it's not that I know the full story, but I think that there will be a naive nerve which would look at strict functors. And this one is good for certain things, but it's not a right equivalent functor. So if you start with a 2 category that has non-invertible stuff, invertible stuff, then the result will not be a 2 quasi category. So instead, Alex Campbell studies this functor. This nerve, I think, is due to Leinster, and this one is right equivalent. So it makes a lot of things easier. But I don't know if you put pseudo, if it would still be, like, I don't have a feeling for whether it would be right equivalent or not. Victoria, do you have any idea?
Sorry, I don't remember what Alex Campbell does precisely. So, yeah, I also don't have a precise feeling on this.
I mean, I suppose if you want that nerve to be a fully faithful inclusion, at least homotopically such, you should take pseudo instead.
It's possible that I misremember, and maybe he does take pseudo. It's possible. Yeah, I wouldn't swear on it. Yeah. Maybe he takes pseudo actually. So yeah, I don't know. We should.
And then, if I may ask another question, this is something that I've already asked Victoria, and she answered. But then I came up with a follow-up question, but I forgot to ask it. So I'll ask it now, if I may, so that you're both here and you can answer. So at some point, Victoria, you mentioned that you use the projective model structure on θ2 spaces, possibly Θn-spaces, and then prove that one of the maps that Martina mentioned is a left equivalent functor, I think, with respect to that. So I was wondering, when you take the projective model structure, you don't know that it is left proper, right? Am I right? I think you don't know that it is left proper necessarily. And so I was wondering how you deal with the localization in that case.
Good question. Yeah, I don't know. I don't remember now.
Because if you take the injective, then it's fine and you can localize, and that's usually the.
So you're saying there
that's the usual way.
You're saying there may be issues in that we can't localize.
The theorem that assert the existence of the localization usually rely on left properness. Though I'm not saying it's necessary, but my question is how you deal with it. It's just a curiosity.
I think we're using. Sorry, I think we're using an order result by Hirschhorn, but I would need to look up the precise thing. Yeah, so I think I don't have the details on at the top of my head, but you're right that this is something which should be addressed in more detail. Yeah. if I remember correctly, there's a version of with cellularity which Hirschhorn has for localization, but yeah, I'm not firm on the details right now.
Okay, thanks.
Yeah, thanks, me neither. We'll figure it out.
Thank you, Eduardo, for your question, and Victoria for your contribution. If there is anyone else that has questions for Martina.
Can I ask a question?
Yes, you can.
Well, hi, Martina. Thanks for your
Hi.
talk. So I would have expected that complicial sets would be kind of the best model in which to study the join because of the way that the join works well with simplicial sets. But you said that it's pretty badly understood, even in the case of complicial set. It's better than the Θ-spaces set case, but still pretty bad. So can you say more about that?
Yeah, so I don't remember exactly what the issue was, but the point is that there are two different joins that you may come up with, and one of the two can be implemented and the other one cannot. Like when you want to build a join, there are two parameters that play a role. And one is related to the direction in which you fill with the cell that you put inside. Like when you work with complicial sets, you decide in the beginning on whether when you have a two simplex, you decide that the arrow points up or down.
Yeah, it's like the
and
street
that's the
orientation or the other.
I think you can choose both, but the point is you choose one of the two and you are going to get for free and well-behaved a join that is compatible with that one. But you could also imagine a different join that instead wants to implement that when you join a one simplex with a zero simplex, gets an arrow point in the other direction. And this one is something that you cannot implement there. So to be precise, there will be two types of joins that you care about, and complicial sets buys you one of the two, but not the other one. So if you wanted the other one, probably you would need to apply some self-equivalence that changes the convention. And then in the other convention, you would get the other one.
Okay, yeah, makes sense.
If I may jump in, sorry, just to follow up on what Martina said. The choice of the direction of the two simplices is forced by also other choices that have been made, for instance, in the coherent nerve for simplicial categories and so on. But there is a way of sort of solving this issue of having two different joints by using the great tensor product.
Yes.
This is something that's part of an upcoming work of ours. And essentially, with using the great tensor product, you can build more symmetric versions of drawing, which take into account both directions for the laxity.
Yes, and indeed, that's the way we understand all possible varieties of joins as like I guess as suitable quotients of a great tensor or something. Like really, you should implement them as a fat join rather than as a non-fat join, and the fat join is obtained using the great tensor product. So in this sense, the great tensor product, as soon as that one is available, then you can also understand all varieties of joins.
Thank you, Amar, I think, for your question. And now, unfortunately, I have to close the discussion for Martina. So